Alright, welcome to the AQA AS Chemistry video. Today I'm going to be doing a video on ionization energies and the factors that affect ionization energies. So let's get straight into it. So the equation for ionization energy. The ionization energy of an atom can be well defined by its ionization equation. So the electron, so in ionization is the reaction where one electron is removed from an atom, and there will be one electron that's found in the product of the equation. So we'll always have an electron term on the right hand side of the equation. The charges, xn plus, and then it goes to form xn plus 1, because the charges on the atom must be understood during this reaction, and during the ionization we remove an electron from the atom. As the negative E minus is removed, the atom's charge will increase by 1, and the second ionization, for example, the second ionization of Na converts Na plus to Na2 plus. Sorry, I couldn't get that as a power, but Na plus to Na2 plus, right? And that's the ionization there. This is not the full equation, but just to show you that as you're losing an electron, your atom becomes more positively charged, right? So if I have, say, helium, right? 2 electrons, 2 protons, neutron top. And I had that's helium, right? If I was having the ionization of helium, I would be I'm putting in energy to remove an electron from this helium, having E here, right? And you now you have one less electron, therefore your overall charge is a He plus. Because now you only have one electron now in your atom, and one electron that's getting released. So your product would be a He plus plus an E minus, right? Because that's what you're forming. And so if I was to do the second ionization, if you had a Na plus, go form an Na2 plus. Now there's a 2 plus charge overall, because there's 2 more protons than there are electrons. State symbol. So the ionization energies are always defined as being in the gas phase. So the atomic species of any charge on either side of the equation will have the state symbol G, which for gas. However, we don't define the state of an electron. It doesn't have a state symbol. So the overall equation, how we'd write these as an overall equation would be xn plus, so whatever our original atom or ion is, xn plus, and that's in the gas phase, goes to form xn plus 1. It'll be from each ionization, you'll be gaining a plus 1 charge in terms of how your product will be represented, because you're losing an electron. You're losing 1 electron from each ionization, and therefore your product will always be the charge on your product will always increase by 1. So it'll be xn plus whatever, or just xn to form xn plus 1 and have a positive charge, of course, because it's more positively charged now, plus an E minus. So putting all these 3 features together, we gain the ionization energy equation. And this is best known by a few examples. So if I was to do the first ionization of Na, right? I want you to, now that I've given you this equation, I want you to write out what the first ionization energy equation for Na is. Pause the video now and do the second ionization energy equation for Mg. So just do these 2 questions here. Pause the video now and do the question. Alright, come on, I assume you've done it now. So how I would write this is that you have your Na, the first ionization energy, so it would just be Na as it is in the gas phase. It's always in the gas phase, and that forms Na plus gas phase plus an electron. And if I was doing the second ionization energy for Mg, which means that I'm forming, notice with the ionization, your ionization in terms of your product will be, so this is the first ionization, we mean our charge will be plus 1 on our product. So if you ever get confused between first, second, so I don't know how to do it. This could be, it doesn't matter what this one, even if this was if you have an atom with 30 electrons, right? And it has the 30th ionization energy, you know your product is going to be 30 plus. So whatever your ionization here is, that's actually going to be your charge. I'll probably say that later on in the video as well, but I thought it'd be easier for you to understand. And your product is, your reactant is going to be -1. So for the second ionization energy, which means our Mg is actually Mg1 plus or Mg plus. Obviously it's in the gas phase, and that forms Mg plus in the gas phase. Mg2 plus, my bad. Mg, let me actually get this way. That forms Mg2 plus gas, in the gas phase, plus an electron. So Mg plus in the gas phase to form Mg2 plus gaseous Mg2 plus ions plus an electron. Right. Ionization energies. A specific volume of energy is needed to remove an electron from an atom or ion. So this is, as we said before, that's our general equation for them. So the first ionization energy, it's going to be here. The first ionization energy is the energy required to remove, and this is a definition they actually need to know for exam. Actually, they always ask in the exam. It's always a one. I don't say always ask it, but or at least something like this. To say, what is the first ionization of this, for example, and it's like, or say define it. It'll be, so the first ionization energy for any atom is the first ionization energy. Put this in brackets here, actually. It's important that you know that. Oh, I can't even put that in brackets. No, I can't. Anyway, but the first ionization energy is the energy required. Let's say. Yeah. The energy required to remove an electron from every atom in 1 mole of atomic gas to produce 1 mole of unipositive gaseous ions. So it's the energy required to remove one electron from every atom in 1 mole. What's 1 mole here is important. 1 mole of atomic gas to produce 1 mole of unipositive gaseous ions. So basically, removing an electron from 1 mole of atomic gas to produce 1 mole unipositive gaseous ions. And if I was to do this, the second ionization energy, I mean, you guys could probably see what it is. You could just probably write this out, but X plus in gas phase to form E minus plus X2 plus in the gaseous phase. Alright. The second ionization energy is the energy required to remove an electron from every ion in a mole of unipositive ions to produce 1 mole of dipositive gaseous ions. And the third ionization energy, so you can see from the last one here, now that we've formed unipositive ions from the first one, now if it's to do the second one, removing electrons from the unipositive ion to form dipositive gaseous ions. And if I was to do the second ionization, the third ionization energy, so it means you have a 2 plus gaseous, so X2 plus to form form an electron plus X3 plus. Now the third ionization energy is the energy required to move an electron from every ion in a mole of dipositive gaseous ions. So it's removing an electron from a mole, removing an electron from every ion, every dipositive ion. So it's to remove an electron from every ion in 1 mole of gaseous dipositive ions to form 1 mole of gaseous tripositive ions. And in the fourth ionization energy, I think you can already see where this is going. It'll be X3 plus gas to form electron plus X4 plus, X4 plus. And I mean, you could probably do this yourself because I think I should have just got you to do it yourself, but you can already see the pattern. If I was to do, I haven't even wrote it down here, but I can tell you, the fourth ionization energy is the energy required to remove an electron from every ion in 1 mole of tripositive gaseous ions to form 1 mole of gaseous quartz positive or tetrapositive ions. I don't know how to say it would be quartz port positive, whatever. But you get the point. It'll be four. It'll be a 4+ charge. It's removing an electron from. So it's the energy required. It's always the energy required because there is an energy requirement. It's kind of like an activation energy, really. It's the energy that's required to remove an electron from every ion in a mole of tripositive gaseous ions to form 1 mole of gaseous quart positive ions. It'll never get to this part, but you need to understand what's going on here. So therefore, using that understanding, we can just say the nth ionization energy can be represented by this equation, right? If we're doing the nth ionization energy, x n minus 1 plus goes, and in the gaseous phase, goes and forms an electron. You get an electron out here, and that's what you have to write for that. And x n plus in the gaseous phase. And it applies to anything. If it's just I could pick a random one. Even if I did x to the power of 127, right? Pick a random one. The idea still applies. If it was the 127th ionization energy, in theory, this would be 127, an electron, and 126, right? I could do any example here, but the whole idea is you get the point that it's going to be from one. You're always removing an electron and you're forming a more positive charge, 1 plus extra positive charge. And so it's going to be 1 less from the number of ionization that it would be. So overall, we can form this equation shown above for the ionization, for the nth ionization. Be aware the value of n for nth ionization is the value of the charge on the ion in the product. Great, now we're going to go to the next part of the lesson, which is factors affecting ionization energies. The main factor affecting ionization energies are the nuclear charge, the distance from the nucleus, and electron shielding. All right, so let's get on to this first part here, which is the nuclear charge. So distance from the nucleus, sorry. I'll get into that part here, actually. So the first part is nuclear charge, but first of all, we need to understand distance from the nucleus. So electrostatic attraction decreases sharply with distance. So first of all, understanding what electrostatic attraction is. Electrostatic attraction is the attraction between the positively charged nucleus, so between the protons in the nucleus and the outermost electrons, or the electrons. It's just the force of attraction between the positive protons and the negative electrons. And this electrostatic attraction decreases sharply with distance, which means that less energy is needed to remove electrons that are further away from the nucleus. So the further away an electron is, the weaker that electrostatic attraction, and therefore less energy is needed to remove that electron from the nucleus. Meaning that as distance would increase, or proximity increases, the ionization energy not proximity increase, sorry. As the distance increases, ionization energy would decrease. There we go. So as you get further away, as I said before, there's a weak electrostatic attraction, the ionization energy will decrease. In practice, this means that the higher the principal quantum number, so remember from the last video we said each energy shell represents a principal quantum number, or we can just call it an electron shell, really. The higher that is, the higher the principal quantum number of an electron, the lower the ionization energy. Okay, I'll go to nuclear charge now. Now I'm going to go to nuclear charge. The greater the number of protons in the nucleus, the greater the attraction of the electron to the nucleus, because it means a greater attraction of electrons means more energy. So this one here was saying that if there's more positive charge, there's that feeling of that effect of that electrostatic attraction will increase because there's a stronger nuclear charge. So there's a more positive charge, so there's going to be a more of that pulling. There's a stronger effect there's a stronger pulling effect, or stronger attraction of those electrons to that positively charged nucleus. They'll still stay in their relative electron shells, or in their fixed distances with the nucleus, but they're more strongly attracted to that nucleus now. So that electrostatic attraction is stronger now, and therefore, if there's a greater attraction of the electrons, This means that more energy is needed to remove an electron, and therefore the ionization energy would increase and get greater. I don't know why I did it like that, to be honest. I don't know what was going on with that. The next part of it is shielding. I'll do shielding next. I don't know why I did it in that order. I should have done this part. I did this part first. But yeah, anyway, you get what I'm trying to say now. I did distance from the nucleus first, nuclear charge second. Now going to go on to electron shielding. Clearly, as you can see, I can't arrange video as well. Shielding. So the greater the number of electron, what electron shielding is there's so I'll just say it first. The greater the number of electrons between the nucleus and the outer electron, the lower the effective nuclear charge, because the positive charge felt by the electrons is reduced by the electrons in between, meaning that the greater the number of electrons, the lower the ionization energy. What does this all mean? Great. So I'll show you. You have your. I'm going to do only a part of it. Say this is your nucleus, and here is the electron that is trying to attract, right? Well, I should probably do a bigger nucleus, right? Let's just, let me make this a bigger nucleus, right? This isn't, I'm just doing this for a rough example. And that's the electron that's trying to attract. Electron shielding would be, obviously that's not, if this is the outermost electron, right? There's going to be other electrons in between it, right? There's going to be electrons here, 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 for example. That's just a rough example I'm trying to say. These electrons, this is called electron shielding, where the other electrons between the nucleus and the electron that you're trying to attract. Let's just say this is the outermost electron, but it could still apply for this electron here. But the example is this electron here. These electrons are shielding this one, are acting as a barrier between this electron here, so this electron here and the nucleus. Because they're all negative, all these electrons are all equally negatively charged. So therefore, remember, electrons repel each other. Electrons repel each other. So because of that, they weaken the electrostatic attraction between the nucleus and this outermost electron here. So when there's high electron shielding, there's a weaker attraction between nucleus and the outermost electron, and therefore less energy is needed to remove this electron. Therefore the ionization will be less, and that's what we're trying to say here. So the more electrons the larger atom is, the more weakly felt the more weakly felt is the attraction between the nucleus and the outermost electron, because there's a lot of electron shielding. So these kind of repel. They block. They kind of think of it as a barrier. They block the attraction between this outermost electron and the nucleus. That's what's really happening. All right, I'm putting this here. So if I was to sum up everything that I've said right now, the factors affecting ionization. I definitely waffle way too much, but making sure that everyone gets the point. So the factors affecting the ionization energy. So we said before, the electron's distance from the nucleus, and the greater distance decreases the ionization energy. So the greater the distance, I'm being more serious on the side. The greater the distance, the lower the ionization energy. There is a notation for ionization energy. Do I want to use it? Yeah, I could use it actually. Ionization energy is referred to as this. But I'll write it like that. And then the next stage is nuclear charge. The greater the nuclear charge, the higher the ionization energy. The higher the ionization energy. And therefore, and more shielding, the more. So the more shielding, So as with shielding, the more shielding between electrons, this decreases the ionization energy. The more shielding would decrease the ionization energy. So there's actually other benefits of having having shells. So ionization energy is actually very useful for, I believe, Niels Bohr, who created the idea of electron shells. Ionization energy is a very useful way of actually proving that there are electron shells and provides evidence for it. So the ionization energies can be used to show the presence of shells in an atom, so with using successive ionization energy. So if we got this, let's get this diagram here, right? This is for calcium, right? So besides shows the trend in successive ionization energies of calcium, and this would form a crucial piece of evidence for the shell's structure of the atom. So we got the ionization energies in each order, so the first, second, third, fourth, so on and so on, and we plotted them on a graph. So this would here represent the energy or enthalpy, right? Again, energy, right? Energy here, and then the successive ionization energy. So from 1 to 20. What's important to understand here is that there's jumps. The reason why this provides the evidence for it is because if you can look here carefully, there's jumps in between at regular intervals. There's jumps before activation energy. So if we remember our, to break down this trend, I'll get down the electronic configuration of calcium, which is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. The reason why I understand, look at the ionization energy. Obviously, they're going to increase, but as you can see here, is 1, 2, a small increase from the 4s2, so going from 4s2 to 4s1, and look, then there's a massive jump from the 4s2 to 3p6, and then obviously there's going to be 1, 2, 3, 4, 5, and 6. Have I made that wrong? Yeah, no, that is 6. Sorry, my bad. 1, 2, 3, 4, 5, and 6. There's a small jump here, but that can be, it's just a mini jump should there's a change in the subshell. But as soon as it gets from, because there's only small jumps from 3p to going down to 3s, but there's a massive change as you go from a massive change to each shell. So if you see between subshells, there's only a small change, but we do know there is enough of a change for you to say there are different subshells here. But to show that there's a massive change between each, so from the fourth shell to the third shell, there's a massive jump, and then going from the third shell to the second shell, there's a massive jump here, and and then you can see here 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, and this is how we kind of get the 288 rule. But we know the subshells, but to show that understand, look, that as soon as it gets from the second shell then to the first shell, massive jump. This shows us there must be shells, and in regular intervals, because they can't just have 2 and 8 and an 8 here and another 8. Like there's shells. So that's kind of why successive ionization energies are useful. Its first ionization energy corresponds to removal of an electron from the n equals 4 shell. it's third. That's what is here, and so the third ionization. When you've done the third ionization energy, the reason I say all of this shit is because, sorry, I swore, but the reason I say all of this is because you'll get a question in the exam, and it'll say, it'll be a question of, actually, I have an example here. Don't know if it's on the first question, but they'll ask you which of the ionization energies. They'll give you 4 examples, right? They'll say 1, 2, 3, and 4, right? Between these 4 examples, which one will have, between the 4 ionization energies, which one will have the highest jump? And it'll be the third ionization energy, because you're going from, in the third ionization energy, you're removing an electron from the third energy level. So that's is going to require more energy because it's in a different shell, and this shell is closer to the nucleus. So therefore, more energy. That means that there's going to be a stronger electrostatic attraction, alongside the fact that it's now more positively charged because you removed 2 electrons, but you're removing an electron from another shell that's closer to the nucleus. Therefore, there'll be a big jump between the ionization, or a massive difference between ionization energies from the third and second ionization energy. So this will N equals 3 will have the highest ionization energy, highest jump, in terms of these two. If you get a question like that. And between the 4th to 10th ionization energies, the electrons being removed from the N equals 3 shell. So between here to here, it's pretty much the same. So they're pretty much all removing electrons from the same energy level, or the same shell, really. And then the 11th ionization energy, if it was to do that same principle again, it would be a massive jump again, because you're moving it from the N equals 2 shell. Yes, and you can see the pattern, and you can just see this pattern above here. And if I was to explain the patterns, that ionization energies increase with proximity to the nucleus. So the N equals 1 shell will have a higher ionization energy than the N equals 2 shell, because the N equals 1 has a higher proximity compared to the N equals 2 shell, because it's closer to the nucleus, right? And N equals 2 shell will have a higher ionization energy than N equals 3 shell, and N equals 3 shell will have a higher ionization than N equals 4 shell, and so on and so on and so on, etc. Within the N equals 2 to 3 shell, you can see the pattern in terms of the fact that the successive ionization energies will. And this is what Bohr discovered, right? This is what Niels Bohr discovered, that it's kind of really beautiful pattern, is that the successive ionization energies will rise as the ion becomes more positively charged, and they rise in regular intervals. So it's always going to increase because there's a higher the electrostatic attraction increases, so more energy is needed to remove the electrons, but they remove in regular intervals. You see this, there's a pattern to it, and that's what allows them to say, it's just, this is the evidence to say that there are electron shells. And yeah, that is it. That's all that I have for today, unless I can find that question. I probably won't find the question, but if I do, in fact, I'm going to make a video after this. Yeah, I'm going to make a video after this, kind of going through some questions. Yeah, actually, it's here. It's literally here. It's not the exact question as I said before, but they'll have an example of they'll have an example of a question that should have a massive jump. For example, boron. I don't know where that is in the periodic table. It's a, I think it's in N equals 2. I think it's in the second group. If I'm wrong, I might be wrong. No, it's in N equals 3. So it means that boron is in the third period, or in group 3. Not third period, sorry. Periods are this way, sorry. It's in the third group, or in group 3, which means that it wouldn't have a massive jump, but it would be probably, I don't know, let's say 5,000 or something like along those lines, something like that. But you can see it'll be something around 5,000, 6,000. The jump between 5,000 to the next, this isn't a real exam question, by the way. This is a real exam question they'll give you. But the jump from the third ionization energy to the fourth ionization is massive. You know, if I'm right with 5,000 roughly, that's 20,000 kilojoules increase, and that's because it's in group 3. To remove an electron to the next energy level, you're going to the next energy level. So that has a higher proximity to the nucleus, and therefore more energy is required to for ionization. Hopefully this video was actually helpful and not me talking for way too much. But yeah, that's what I have to say. That's it. Bye.